final type of natural radioactive decay is alpha decay. Those elements that go through alpha decay are beyond the band of stability. And if you take a look, you'll see that the atomic number, the number of protons, only goes up to number 80. We have elements that go through 109, so the rest of them are somewhere other than on this chart. Alpha decay generates alpha particles. Alpha particles are helium nuclei. So they're relatively large and massive. They have 4 nuclear particles and a +2 charge. So they're large and they're very charged. So if the isotope wants to get rid of a big chunk of the nucleus because it's too big, an alpha particle is generally the way that it chooses to go. It turns out that elements above number 83 are all radioactive. Element 83 is the last isotope that is stable, last element that has stable isotopes. Anything higher than 83 is a radioactive isotope, which means all of them are unstable, all of them are going to want to go through radioactive decay, and the preferred method for these large isotopes is alpha decay. An example of an isotope that goes through alpha decay would be radon. We start with radon-226. Radon has an atomic number of 88, so we're going to kick out a helium nucleus, so a mass of 4 and a charge of 2, so that means the isotope I form has got to have 4 less atomic particles, nuclear particles in it, so it has a mass of 222, has 2 fewer protons, so it's going to have an atomic number of 86, and that element is radon. Again, as with the other types of radioactive decay, we're going to get gamma radiation as part of this process. Those are the 3 naturally occurring types of radioactive decay. The other 2 types of nuclear reactions we're going to look at are not decay reactions. One of them is not naturally occurring, and that's fission. Fission is a man-made process that's very different from decay. What we're doing with fission is we're breaking a very large unstable nucleus into 2 new elements approximately the same size, and the way we're doing it is we're bombarding it with a slow neutron. So we have 2 particles on essentially our reactant side, the large unstable nucleus and 1 neutron. And rather than having the neutron slam into the nucleus quickly, much as you would break up a billiard setup when playing pool, you're going to have the nucleus actually try and absorb this slow neutron, and the effect is that it's already unstable, and this is the one more particle that causes it to break apart, similar to adding that one final card to a house of cards and the whole thing collapses. So we have this very unstable nucleus, we add one more particle, and it causes the thing to break apart. Fast nuclei, fast neutrons would just bounce or ricochet right off of these things, and it would not cause them to split. Most common example for looking at fission is uranium-235. Uranium-235's atomic number is 92, and we're going to add a slow neutron to it. So our total mass on the left side is 236, our total charge is 92. And again, when the uranium is split, it breaks into 2 isotopes approximately equal in size. Usually when you're given a fission problem, one of the isotopes is specified. From that, then you can determine what the other isotope will be. There are actually 3 products when you go through fission. The third product is another neutron. So for example, if we say our first isotope generated from this fission process is strontium-90, that means that our next element has got to have an atomic number that is 92 minus 38. That would be xenon, which has an atomic number of 54. Xenon's mass depends on the number of neutrons we generate. In general, for fission reactions, we can generate 1, 2, or 3 neutrons. And depending on the number of neutrons we generate, if the isotope of strontium has been assigned, then our choice of number of neutrons will affect our atomic mass of xenon. So 1 neutron gives me atomic mass of 145 for xenon. If I end up choosing 2 neutrons as a product, then my atomic mass of xenon will be 144. If I end up choosing 3 neutrons as products, then the atomic mass of xenon will be 143. In each case, the mass of strontium plus the mass of xenon plus the mass of however many neutrons I have has to add up to 236, which is my total mass on the left-hand side. So I'm adding a slow neutron, and I get isotope of strontium. That was the one in this problem that was specified, so that allows me to deduce that I am forming xenon as my other product, along with the neutrons. I can choose how many neutrons. That affects the atomic mass of the xenon, which is my second isotope. The last type of nuclear reaction is fusion. Fusion, it goes on naturally in the sun and any of the stars, and it is the combining of very light nuclei, usually helium and hydrogen, to make heavier elements. All the elements in the universe are in fact created by fusion. Hydrogens combine to form helium, heliums combine to form beryllium and boron, and those combine to give us carbon and all of the elements. They're generally formed as heavier elements in larger numbers when the large stars go through nova or supernova process, and there is a large rate of very fast fusion going on. Fusion process again starts with hydrogen, so I take 2 hydrogen isotopes, most common form of hydrogen. When I combine them, I get another isotope of hydrogen. This is heavy hydrogen or deuterium. I also kick out a positron. Along with this reaction, and fairly quickly following it, I take 2 of these deuterium isotopes and combine them. This combination gives me helium, mass of 4, atomic number 2, and I get gamma radiation. One of the benefits of fusion is there are no radioactive particles that are generated. All of the other types of radioactive decay have the potential to generate radioactive particles. Fusion does not. That's why there's been so much research looking into fusion to generate more safe energy sources. This is in fact attempting to go on with our power plants and military nuclear generation, medical and research nuclear reactions that are being studied. Nuclear waste is being generated, and since the decay rate is sometimes millions and billions of years, it has to be stored safely somewhere. So coal mines, sulfur mines, salt mines have been explored and looked at, considered as being storage sites for this radioactive waste.